Okay, so first of all, any questions from yesterday? Everything clear? Okay, and of course you can go back and look at the lectures or discuss with each other and see. Okay, okay. So today's plan is that, so what did we do yesterday? So yesterday I basically spoke to you only about one evolutionary process, namely stochasticity or random genetic drift. And the key thing, that just one line lesson that you are supposed to remember is that if you have drift, only drift, then there will be an absorption. You will have either fixation or loss of an allele. Okay, so that was this one line lesson. And today what I will do is make things slightly more complex. So we are done with drift. Okay, so today I'll do drift plus selection. I'll then also do drift plus mutation, and then drift plus selection plus mutation plus recombination. Okay, so let's see how it goes. So this could be too much, in case you feel it's too much or something. If you ask me questions, I'll slow down, and it's good for you, good for me. Okay, so please, like yesterday, please ask questions. Okay, so we'll start with drift plus selection. So no mutations again. And like yesterday, we thought about this population of size n, a finite population of size n, okay? And there were these two types, A1 and A2. This was two alleles at a single locus. And yesterday they had equal fitness, right? Today, let's say the fitness of this is 1, and the fitness of A2 is 1 plus S. S, as you know, is called the selection coefficient. So if S is positive, then A2 is a beneficial allele. If S is negative, it's beneficial. If S is negative, it's deleterious. And if S is 0, then of course, we are back to the neutral model, right? Okay, so this is a general model, okay? And what do you think will happen in this model? So we have, only difference from yesterday's is that now A2 is maybe less fit or more fit than A1. So then we run this process in our head that we have 3 A1s and 3 A2s, and they reproduce, they make twice the copy, we remove half of them and so on, and look at this eventual fate. What do you think will happen this time? Mike?
You'd expect that if A2 has a selective advantage over A1, it will end up fixing in the population.
Okay, so first of all, even the zeroth order question, will we get all A2s or all A1s? Is that going to be the state in this case? Or is selection going to change that qualitative state? Do you think we'll wind up with some A2s, some A1s eventually? Or we'll wind up with all A2s or all A1s? So let's first get the zeroth order question correct, the answer. What do you think? We'll come to what you for this in a second. Huh? No, so is it going to be polymorphic population or monomorphic? Monomorphic, okay, because it's going to be fixation and loss. That answer has not changed. Now, go ahead. So you said, so she said that if S is positive, that is the beneficial mutation, so A2 is beneficial, then A2 will fix. So my question to you, will it definitely fix? Yes? Those who say yes, please raise your hands. It will for sure fix, because you know it's a good guy. But this randomness, just because you know I'm good doesn't mean I'm successful, right? Right? Something, what is it called? There's a many a slip between a cup and the lip, right? So all the randomness will come in, right? So this is the key point here. We think, and this is the obvious thing to think, no, it's a beneficial mutation. So you think, yeah, it will fix, yeah, it will spread. But no, there's drift. There's only a chance, less than 1, that it will fix. So even if it is good, the P fix prob that A2 fixes, okay, I'll write the expression a little later, is less than 1. It will not fix for sure. It can get lost. This is a very important lesson that you're going to learn this. So lots of things you can understand using this little funda. Okay? Okay, so now, again, let's ask, so this was the case when S is positive. Suppose A2 is deleterious. So I want to hear from this section. Somehow, I am not getting any answers from you guys. Suppose A2 is deleterious. Then what do you think will happen? What's your intuition? Can you tell me? What do you think? You? Yeah, good. Because A2 is bad, doesn't mean it necessarily gets lost. It can, A1 can get lost or A2 can fix. So A2 is deleterious, so you expect A2 might, not necessarily, might get lost. Or might, might fix. Okay? So its probability of fixation is more than 0. Right? It's deleterious, yeah, it's for the same reason. If it is deleterious, by chance, it can fix. That's the whole thing. It's the whole point here. Okay? So our usual intuition, good, will fix, bad, will not fix. No. Okay, and now I'll make this statements more precise. Okay? So, okay, let's just, let's just do slightly more qualitatively. What do you think? If I have a very large population, I have some population of n size, and I have a larger population, in which population would A2 fix if it's beneficial? Larger population or smaller population? Larger population has a higher chance of fixing. What about deleterious one? Where is it more likely to fix? In smaller population, large population? Smaller population, right? That's the sort of intuition, right? Okay, and there's a nice, slightly complicated, but it's still a very classical, it's a famous formula in population genetics for the fixation probability. So I'll write this formula for you. It's for haploids, but you can write for diploids also. Okay, so this is due to Kimura. I think 55. Okay, so this is a long known, very long, known for a very long time. And one thing I strongly recommend, whether researchers, biologists, chemists, whatever, it's a very good exercise to plot things, to plot this formula. So you have two parameters here, S and N. Use whatever software you like. If you're the pencil paper types, draw it and see if it gels with your intuition that you told me. So this is the quantitative formula, and it has been derived using this so-called diffusion theory. So we will not bother too much about that. Okay, and this is when I have a single A2, but if I had n A2s, little n A2s to start with, it just becomes this. Okay, so this is known for a long time. Okay, so but let's just do a little bit more. So here, so you will see in books in literature this phrase called weak selection or strong selection. Okay, what does that mean? The selection coefficient is typically less than 10 to the minus 2 or so. Right? It's a small number. What does it mean, weak selection? So there's one very important thing, and I'll keep repeating this point again and again. Whenever we say something is weak or strong, big or large, big or small, it's relative to something, relative to some other scale. 10 is much larger than a micron, but is much smaller than a million, right? So you have a comparison point. So here, when we say selection is weak, in these diffusion theories, it comes from this NS which is sitting here. So when we say if selection is weak, it means S is much smaller than 1 by 2n. So 1 by n, people say like sort of a power of drift. Okay? So I'm saying selection is weak or it's nearly neutral or so not neutral but nearly neutral, it means selection coefficient is much smaller than 1 by 2n. Okay? And similarly, strong selection is the opposite limit, in which S is much larger than 1 by 2n. So whenever somebody says selection is strong, weak, what you have in mind is comparison to something else. And here, the comparison to drift, okay, which is 1 by n. Is it clear? Okay, and I will keep repeating this point in another context also. Okay, so for deleterious mutations, I'll just explain this formula a little bit. So if, and let's just do for 1, there's a single copy. So if we have S positive, that means beneficial mutant, you can analyze this formula, okay? And it turns out it can be approximated by twice the selective advantage. This is also a very famous formula due to Halden. It's a limit from this general formula, okay? I forgot the year, it's the 1930s. But if you have deleterious mutation, it's not just 2 times its value. It's a different dependence. It's roughly the amount of S, the amount of, S is negative. So mod means, if it's minus 0.1, mod S simply means, okay, maybe I'll write this. So if S is negative, it's e to the power 2ns. For deleterious ones, your intuition was, you said that, it will not fix, right? So whenever we are dealing with things which have deleterious or neutral, we have to get n into the picture. For beneficial ones, sometimes we can get formulas which are independent of n. Okay, that's one thing. But the point is that the dependence on S is very different for the beneficial and deleterious. One is linear dependence, other case is exponential. Exponential decays are very fast. S increases linearly. In the beneficial, it's a very fast decay, exponential one. So please get some intuition into, or some feeling for these functions. What's the exponential function? How fast does it decay? And I strongly suggest you to plot these things and see. Okay, so I hope you played with this simulator. 1 second. And again, that should again help you to see these answers. Okay, yeah.
What is the range that S can take?
S is, suppose I take, for the formalism, typically S is small, less than 1. But suppose I just push it, S to infinity, right? In that case, this fixation probability of a positive mutation becomes 1. Okay, so your intuition that beneficial is good, but it has to be infinitely good to counter the effects of finite population. But in actual calculation, S is less than 1. Actually, it's much smaller than 1. So in this diffusion theory, when we put in things, that's what we are assuming. Any other question?
This is applicable only when S is much less than 1.
Yeah, that's because that's biologically correct. Yeah? Okay, fine. Okay, so selection, this much only I wanted to say. And I'll come to when I put these things together. Now, let me go to the second point, which was, let me turn off selection again. But now, I will talk about drift and mutation. So what I just said here was no mutation. And the state, final state of a system was monomorphic. Either you have all A1s or all A2s. Something else will happen when we have drift and mutation. Okay, so I want to talk about neutral diversity, and associated to that is something called Lewontin's paradox. So we'll come to that one by one. So first of all, let's first see a very simple example. How do we calculate these heterozygosities or measures of diversity? I'll give you this little example. Suppose you give me, you found some genetic sequences of 5 individuals and of a very long sequence, say 500 long sequence. So I have a genetic sequence of 5 individuals, and the sequence is 500 base pair long. Okay, So you collected it and you give me this data. So I'm writing only 4 zeros or ones. There are a lot of dots here because I'm interested in calculating diversity. So dot means that if I looked at this locus, first locus, all of them had say 0 or 1. This site was monomorphic. So I actually have 500 sites, but because they're monomorphic and I'm interested in diversity, I'm not going to write them. Okay? So these are the sites where at least one of them is different from each other. And I want to calculate the neutral diversity. So I'm going to assume this is the null model. It's the simplest null model against which we will compare things. Okay, so I'm going to assume, make the simplest assumption that there is no selection. Okay, so we will say there's no selection. These sequences that you have given me are neutral, and I want to find how much diversity there is. A measure of diversity, because these sequences are different, right? How do we calculate that? So this is the pairwise diversity. So what I'll do is compare first and second one. How many differences are there between first and second sequence? 1. First and third? 1. First and fourth? 2. First and fifth? 1. Right? Then I repeat that. Second and third, second and fourth, second and fifth, third and fourth, third and fifth, third and fifth, fourth and fifth, right? So you can write all those pairs. Okay, I'll write it for you. Please check if I did it correctly. Okay, so this is the total number of differences. I'm looking at average pairwise diversity. Because all of them neutral, I will just average over all of them. Yeah. Yeah. So I have these 5 sequences, and dot means they are the same, and this is where the differences are. So I'm asking how many differences are there between first and second sequence. 1 difference. First and third, 1 difference. First and fourth, 2. First and fifth, 1. Then second and third. Second and fourth, second and fifth. Third and fourth, third and fifth. Fourth and fifth. Okay? But I'm calculating average, right? So I have how many? 10 such pairs. Okay? And it's the diversity over the entire sequence. And I said to you, it's 500. Okay? So this is the sort of the elementary calculation one can do, and some number comes out, something, 0.0036. So that's the kind of thing that one can do. You give me the genetic sequence, I'll assume it's neutral, and I'll just maybe put it in some software or sit by hand and then work it out. Right? You can calculate it. Okay, that's very nice. I got this data, I got some number, but can we understand this number? Why this number? What are the processes which are giving me this variability? If it was only neutral, it was only genetic drift, then there is no variability, right? Okay, so the simplest assumption is that this is drift and mutations. Drift had this effect that it was taking away the diversity. It's reducing the variability because everything is finally becoming monomorphic, right? Whereas mutations will keep coming in, right? So I would assume it's a very long sequence, okay? All of them started as 00000 at some point, but with a certain probability mu, 0 becomes 1. And I'm also assuming that 1 does not become back 0. The back mutations we ignore because it's a very long sequence. Hitting the same sequence twice is highly improbable. It's L to the power minus 2, L being the length of the sequence, okay? So we'll assume that mutations are coming in, okay? And at every site, because of evolution, it's possible everything becomes 1. That I replace by dot, okay? And then new mutations keep coming in. So what do you expect? Drift is taking away the diversity, right? Mutations is bringing it in. So you expect there will be some drift mutation balance. This is different from what we discussed with the drift only or drift plus selection only, where the state was sort of boring state in which it was monomorphic, no diversity. So now we have this mutation drift balance. Or sometimes equilibrium diversity. So this is the diversity which we are looking at large times. There is a lot of interest these days in non-equilibrium diversity. That means while the population is evolving, with time diversity will change. How much is it? And so on. Okay, so which we will not talk about that. Okay, so yeah. So for this mutation drift balance, you can do a calculation, but I'll just skip all that and I'll just give you the answer. So it turns out this diversity can also be related to heterozygosity. Okay, so I did for haploids, but you can do it for diploids. And the answer is given by this expression. For those who are interested in derivations, I will just mention that this derivation is based on something called infinite sites model of Kimura. Okay, don't worry too much about it right now. So this is our heterozygosity, 4n mu divided by 4n mu plus 1. But you see, just like we had this combination coming, n times s, right? Drift and selection. Here also this kind of combination comes, this kind of composite parameter comes. N times mu. Okay? So but now I will repeat the same point. When I say weak mutation, analogous to what I said over there. So weak mutation, weak compared to what? So what I mean is mu is much smaller than 1 by 4n. The power, the mutation rate is much smaller than the power of drift. And similarly, one sec, strong mutation is just the opposite case. Yeah. Is the neutral mutation rate from 0 to 1 at a single site. 4 comes from a calculation for diploids, and n is because of drift. Yeah. Yes, because it's monomorphic. Yeah, sure. And in fact, I will draw ... everywhere. Okay. Yeah. So is this concept of scales, when we say strong, it's not about the absolute value. It's relative to something. It's a really important thing. Okay? To make sense of, when one says small, weak, compared to what? So now, we can now look at this. If mutation is very strong, lots of mutations are coming at some high rate, you expect diversity should be very high. Indeed, this H, if you work out, for this case, H will go to 1, right? As you expect intuitively also. But if 4n mu is much smaller than 1, then diversity will be low. And as you said, if it is very small, it's actually close to 0, right? But typically it is small, and the formula therefore reduces to 4n mu. Okay? So diversity for very large mutation is 1, a very small one is about 4n mu. Okay, so that's very nice. So we have this little formula due to Kimura, and it's very easy to calculate a pairwise diversity if you give me genetic sequences. Let's do much more. Let's just take all kinds of organisms, all kinds from different taxa, this and that, and just calculate this kind of neutral diversity and find and see whether it matches with Kimura's prediction. Okay, so that's the graph that I have sent you in Slack. So I will just draw it for you so that you're not too distracted. So this is, I'll explain. So Levantine is a famous biologist, evolutionary biologist. He passed away a couple of years ago. But his work, this question that I'm going to describe to you, has influenced last 50 years of work. Okay, so I'll explain that. Okay, so if you see in your Slack, you'll see I'm plotting log, ln stands for log. If you don't like ln, I'll write log for you. Okay? So what is plotted on the x-axis is the log of the census population size. And the y-axis is log of that kind of pairwise diversity. And you see the scales. This lies between 10 to the minus 4 to 10 to the power minus 1 or so. And the scale on the x-axis goes 10 to the power 4 to 10 to the power 10 or 16. So if cumulus prediction is correct, we expect a linear answer, right? Okay, something like this. But the data is confined to a narrow strip. So only about 10 to the power minus 2 to 10 to the power minus 3. So pairwise diversity is so much squished. Your census population size is 12 orders of magnitude. And the pairwise diversity across all kinds of organisms is just 1 order of magnitude, right? Kimura's neutral prediction would have told you this. It should increase as the census population size increases, it should increase. Okay? So calculating using this sort of method. Okay? So therefore, question is why? So this paradox that why the neutral genetic variation is so small, right? So that's called Lewontin's paradox. And there has been this work, so this is 1974. So we still don't know completely how to understand this quantitatively. And I've sent you this review of Charsworth and Jensen. It's on website of ICTS. Okay, so that goes through, it reviews some of these reasons why or how we can probably explain. Unfortunately, we still don't have a complete answer, but I will briefly explain some of the reasons that may be responsible for explaining this. Oh God. Okay, so let me explain the ones that I'm not going to discuss in detail. So one reason is simply demography. So the idea here is that, it's not the census population size you should look at, but rather some kind of effective population size. And we encountered it yesterday when I discussed with you the Bourie's experiment, because maybe some of these assumptions about random mating, etc., are not valid. Okay. Similarly, demography means population size is not fixed. I took a very simple model yesterday and today also, Wright-Fisher model, exactly n, but of course that doesn't happen. N, population size will fluctuate. It can contract, it can expand, right? Okay, so that would happen. And I'm not going to go to the math, but it turns out with demography, effective population size can decrease substantially. So the idea here is that n, because of these contractions, expansions, and things like that we discussed yesterday, should be replaced by some kind of effective population size, which is typically much, much smaller than n. So yesterday I told you that n effective is 30,000, so I look back, it's about 10,000 for humans. Okay? Yeah, so that's one reason. So the idea here is that, it's not 16 or 12 orders of magnitude, it's something much, much smaller, and then maybe that's the reason you have a smaller range for the pairwise diversity. People have done a lot of work, and it is a very important factor, but right now, the current status is that quantitatively it still does not capture this data. It does, helps, it does help, but not completely. So there's a further idea due to Lynch. So he says that, the mutation rate is correlated to the effective population size. So there are certain fits they have done, and they find that any decreases is anti-correlated to the effective population size through this power minus 0.7, which means the pairwise diversity n mu would be 0.3. It will grow, but slower than linear, right? Again, this does not explain completely. I mean, it made some, changes, but not quite. Okay, but these two factors are other factors also, and you should read this review that I sent you. But I will focus on is the effect of selection on linked sites. So this is a whole subject in itself. So it's not just about Leventin's paradox. It was motivated partly by this paradox, but it's it has lots of tiny things and lots of questions. So I want to explain that in this last few minutes. So while I'm erasing, maybe you can look at Slack. Okay. So this factor that I want to explain is selection at linked sites. Okay. So here we will have drift, selection, mutation, and linkage. We haven't spoken much or at all, I think, about linkage. So I first need to introduce that to you. So let's talk about a simple model with recombination. So you guys are, of course, experts. So I will say a very simple stuff about recombination. Okay? So I'm thinking of a two-locus model. Again, two alleles at each site. So I have two sites, and first site can have A1 or A2, as we have been doing so far. And second site also can have B1 or B2 allele. Okay? A is for first site, B is for second site. So what are the genotypes that are possible? Yeah, let's hear from others also. I know we will stop the experts from speaking. Non-experts or the going to be soon experts. Can I ask you? What are the genotypes that are possible? So on the first site, I have A1 or A2. Second site, I have only B1 or B2. So what are the combinations that I can make? What kind of individuals I can have? Huh? A1, can you speak loudly? A1, A2. No, first site can have only A1 or A2. Second site can have only B1 or B2. Right? That's the meaning. Is it clear? Okay, you want to try? Yeah? A1, B1. Yeah. A1, B2. A2, B1. Yeah. Is it clear? Yeah, good. Okay. So these are the four possible genotypes we can have. And by recombination, what I mean here is that if I have A1, B1, and let's say A1, B2, with some probability R, these two will break, and when they break, I'll have this stuff lying around, and they pick combinations. So maybe this A1 matches with this B2, and this A1 goes with that B1. Okay? If they go with their own partners, of course, there's no change in the frequency. So we are not interested in that. We are looking for things which will change the frequency. We are interested in seeing those things, right? Okay? So in this case, what this means is you break and swap the genetic material. So if I do that, break it and swap, let's say, the second site, I'll get A1, B2 and A1, B1, right? Yeah. R is the probability of recombination. Is this much okay? Some people look lost. Come on, this will be more tough for me. Yeah. R? It's just one of these popular genetic parameters like mutation rate, selection. and recombination. Maybe there's more details about it, like what determines it, but I don't know. So for me, it's just a parameter. Like mutation rate. Mutation rate, you can go into more and say, what is this polymerase, et cetera, which control it. Maybe there's something more for recombination, I don't know. Is this okay? If these two recombine, these genotypes, has anything changed in the frequency? No. So can you tell me, what genotypes are good? That will lead to some change. A1, B1, A2, B2, very good. So break and swap, right? So you destroyed these two guys and got these two new guys, right? So those are the kind of things we are looking for, okay? So you can work it out, slightly involved, but you can work it out, writing all the frequencies of all these guys and seeing how, the frequency of this combination of this guy will decrease because of this recombination. It can also increase. Suppose I look at the back process, right? What will this give me? A1, B1, A2, B2, right? So then A1, B1 can be increased through this recombination and it decreased through this recombination, right? So you can write down stuff like that, okay? So the reason, yeah?
So when you say R is recombination probability, does it include both of these or only one?
It's the probability with which a break and swapping will happen. Break and swap. That's how at least I understand. They need not, right? Okay, so I'll throw a random number. If R is 0.1, there's a 10% chance that I'll break and swap. Otherwise, they just live their life as they were doing. Yeah? So the reason I wanted to bring this in is to introduce this concept of linkage disequilibrium. Or for short, it's written as LD. So suppose I look at the frequency of A1, B2. So after all that stuff is done, I look at the frequency of A1, B2. If recombination is very high means if it's a probability, it can be at most 1, right? So, but it's sufficiently high, okay? And I'm thinking right now in terms of absolute values. If recombination is very high, I expect that A1 will sometimes come with B1, sometimes with B2, because they'll break and swap and break and swap. Lots of stuff is going on, right? So you don't expect a special preference of A1 with B2, right? It can come sometimes with A1 can come sometimes with B1, sometimes with B2, right? So if there's a lot of recombination, then you expect that this frequency I can write as the product of this each frequency. Okay, yeah. Okay, so yeah, I'll repeat it. I mean, let me finish and I'll come again because I need to repeat it. Okay, so okay. On the other hand, let's say there's no recombination. Then what happens? Yeah, they were together only. What can you do, right? No recombination. Then you cannot do anything, right? So a lot of recombination is that A1. It can sometimes come because of a lot of sex or recombination. It can come with B1 and B2. Sometimes with B1, sometimes with B2, but there's no special preference. It's a random association. Okay? So let me, because you'll see this word, random association. It's nothing special, right? But there is a lot of recombination. If there's no recombination, you are stuck with this one. So the difference between these two cases is basically what defines the LD or the linkage disequilibrium. So F is the frequency. Okay? And it's not nothing special about A1, B2. You can look at all the 4 pairs. That's the definition of LD. You can take any of them, it's the same. Because I have assumed here no selection, no mutation, in fact also no drift, only recombination. But you can massage these models and get the stuff. Okay? So this is the definition of the linkage disequilibrium. So you see, if they are asexuals, right, then if there is a lot of recombination, then there is no LD because of this, right? If there is asexual, then there is a D, non-zero D. Right? So it's a measure of these non-random associations. Okay, and that's very important when we're talking about linkage. The limiting case, the extreme case being the asexuals. Okay, so now that we understand, I hope, what is linkage disequilibrium, okay? It has this property, so we can write down equations, stuff like that. It decays pretty fast if we don't have other stuff like all the mutation, selection, and so on stuff. Just the linkage disequilibrium. So D, it goes like, so E is this exponential functions. If you're not comfortable with it, just go and look at your 12th standard book. Okay? So it's e to the power minus RT. That means it decays exponentially fast, very, very fast it decays. So if there's no sex, there's no recombination. So, okay, sorry. So the time it takes to reduce LD to 0, when LD becomes 0, it's called linkage equilibrium. Right? So in this case, to 0, which means we will be in a state of linkage equilibrium. Okay? So that time is of the order of r to the power minus 1 by r. It makes sense? Because if there's no sex, there's no recombination, time will be infinite. No, you're always stuck with this guy. Right? But if there's a lot of sex, a lot of recombination, in that case, the time is very short. Quickly you get rid of these associations. Right? And it decays pretty fast. Okay? So this is how LD changes with time. So I'm going to use this concept, this idea, when I come back to the selection and link sites. And I want to describe this one process, which again, was motivated partly to describe Leontief's paradox. Okay. So this is called selective sweep. Okay. So let me just describe to you first from a sort of a cartoon. So suppose I have a population in which all individuals to start with, let's say, are neutral. Okay? So which I'm writing the previous sequence I wrote for you, right? It's 4 individuals, 5 individuals, dot, 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 I'm not writing anymore. Okay, these are 5 individuals which have a long sequence and so on, and these are where they are polymorphic, and zeros and ones denote a neutral site. Okay, so all neutral and so on, but let's say at one site a beneficial mutation occurs. At some point with some rate UB, this becomes neutral, selected. And let's say it's a beneficial mutation, okay, at this time. What would happen to this in this case? Let's take the case in which these are asexuals, stuck together, right? It's and also let's say for extreme case, let's say this star mutation is a very high fitness. So what do you think will happen with time? So you expect that these will produce more offspring, right? It has a high fitness. Oh, but yeah, one important thing. What is that important thing? Yeah, but what will it do? Huh? I want to hear from those guys. What can happen? What else can happen? Huh? Yeah, drift. What can it do? Star can get lost, right? So this is the first thing to think of. How can we forget? So one possibility is star gets lost, right? Okay, that's the drift, right? But now let's look at the cases in which it does not get lost. So let's look at those cases. So maybe it came, it got lost. I mean, beneficial mutation will come, no, they're rare, but they'll come. Maybe after 10 years again it comes. And this time it does not get lost. So I want to know what will happen to that. In that case, how will this population behave? So as some of you were saying, it's a good one, and we say that it will spread. It will produce, on an average, more offspring compared to these guys, right? Right? So, and let's say they're asexuals. So they are always stuck together, right? So this will produce offspring, more, and as time goes on, what do you think will happen here? I get, yeah, somebody's saying something. Okay, Shubha knows all the answers. Huh? Say that again. So what do you think the 5 individuals look like?
It will be the frequency of star and what that will be.
Okay, so if I understand you correctly, so we expect this, no? That all of us expect, right? And the third locus will be star because it's spread. But not only that, it's stuck with those guys. Is that Fevicol or something, right? So eventually, if no more, stars and other things happen, okay, this is the fate of my population. So because this linkage, it has dragged along, this because the star was spreading, but the neutral guy is neutral, I mean, okay, it fixes due to drift, but because of linkage, it hitched the ride with this star. And what did it do? Initially, I had diversity, right? We calculated 0.0036 something. But now, what's the diversity? 0. So it's as though because of selection and linkage, the diversity has been swept off. Okay, so that's why it's called selective sweep. Okay, and what has that to do with Lewontin's paradox? Well, that's what we wanted. We wanted to reduce diversity, right? So this is one mechanism which can potentially reduce diversity in a population. Now you will say, oh, but these are not asexuals. There were all kinds of organisms there, right? So therefore, let's now relax that. So we know that linkage disequilibrium decays over a time period of 1 by r. So here in this problem, there we have 2 time scales. One is the time to break association, which is of the order of 1 by r, which is what we just learned. Right? But this guy is not going to just spread in one day, like immediately. There's some time for that. That's the fixation time. Right? Yesterday we discussed that a little briefly. There's a chance of fixation and there's time for fixation. And the other scale therefore is time to fix the star. And this is the competition between these 2 time scales. If the time to fix is taking a million years, associations are broken, there's no change in diversity. Make sense? So if fixation time is much, much longer than time for recombination, then I don't expect diversity should remain same. Right? But in the opposite limit, if fixation happens faster than I can break these associations, then I expect diversity to reduce. Here it was the extreme case in which diversity became 0. But in general, it's a small thing is finite. right? Okay, so one can write down this little formula, and this is the actually formula. This sort of concept has, yeah, okay, I'll just give you one reference here. So formula one can write, and it turns out the change in diversity in that kind of pairwise diversity it goes like e to the power minus r, as we wrote over there, and this t is the fixation time of a beneficial mutation. Those who understand, actually this is called a conditional fixation time because this guy should not get lost. So you don't get lost in this concept, but for those who understand these things, I should say this is the conditional fixation time. Okay? Okay, and this we know the answer for the beneficial mutation. It's this log of ns by s. Okay, so it's not an obvious answer, no, log. There's a simple argument I can give you, but let me not worry about that. Okay, so this shows in this two locus model how the pairwise diversity will decrease. Now, it reduces the pairwise diversity as we want it for the Lewontin's paradox, but this whole problem is very interesting and important in its own right, and it's actually used. So, what people do is, you take a genomic sites, so what I'm plotting is just a cartoon, and they measure, for example, the diversity, okay, so look at some data and measure this pairwise diversity as you did in the example. So they find something like this, a valley in the pairwise diversity. What does that indicate? It suggests to them that at this site in the genome, selection must have occurred. This site, something like that star must have happened. Okay? So people measure this kind of stuff, and similarly LD also, it increases. And this is the diversity. Okay? So these kind of dips in the data, and this is done all the time, okay, is used to locate the sites of where selections happen, and of course the depth of this valley is a measure of selection. If it is more deep, that means selection is strong. If it is shallower, selection is weak, right? Okay. Okay, so I will just wind up with a couple of points here. So let me just define this again for you. So selective sweep therefore refers to a large change in allele frequency. Right? From 1, it has become n. The frequency from 1 by n, it has become 1, no? So large change in the allele frequency. So if I were to plot the frequency of the star, it started like this and became this. This is large change. And it should occur rapidly. Large and rapid change. Why rapid? Why do I say rapid change? Yeah, because recombination will break the association. We have another scale, right? So it should, change its frequency should have be a rapid change. So that's called selective sweep. Okay, and the sweep that I described is the simplest thing. It's called a hard sweep, but there are soft sweeps also. Here I assumed, which I forgot to say, is that the star is a new mutation. So there are these couple of points I want you to remember. Sweep is a large and rapid change in allele frequency due to new mutation. But one can also consider mutation, the sweeps due to standing genetic variation. That's called soft sweeps. Okay, so I will not discuss that. And yeah, sweeps can also be deleterious sweeps. They could be neutral sweeps. Deleterious sweeps means what? The star need not have been a beneficial one. I discussed that simply because it's sort of intuitively clearer. But star could have been deleterious because we know that deleterious mutations can also fix, right? For it's moderately deleterious, that can also sweep. So one can speak about deleterious sweeps. Star need not have any selection. It could have just a special neutral locus. That can also sweep. So Santher is looking at some aspects of neutral sweeps. Okay. So I'll wind up with this question. I think in one of the projects I had proposed this question. So it turns out that this level of genetic diversity, at least in these two locus models, one second, due to deleterious sweeps or beneficial sweeps, it's the same. Same amount of depth, whether it's a deleterious sweep or a beneficial sweep, because it turns out some symmetry in the diffusion theory. Okay, let's not bother about that. So that means I will just know that a sweep has happened because diversity is reduced. But was this star a positive mutation or a negative mutation? How do I find a sign of selection? Right? So that's not clear. Yeah. Selection?
Selection not a part of selective sweep.
Selection is not a part of selective sweep? So it is, star is a selected locus, no?
Right. So, but that's only because the mutation was beneficial. So
Yeah.
selection was acting.
On the star and all the guys which are together with it, yeah.
So when you're talking about deleterious sweeps,
Yes?
those are not selected.
They are selected because it's just negatively selected. It's selected, but negatively. It's a bad guy, but it has a chance because of drift. It has a chance to spread. No, but it has a smaller chance, but it can sweep.
But negative selection would ideally.
But it's the fact that it's deleterious. That means there's selection.
Yes, but the negative kind.
Yeah, but then positive kind is selection. The reason positive one happened is because it will produce more offspring. And now let's enlarge that concept. I mean, I see what you're saying. See, it is a selective sweep because it produces more offspring when it's beneficial, right? Which you agree, and that's because of selection. Yeah, but now let's enlarge this concept and generalize. Why? Why not beneficial? Why we are so hung up on beneficial guys? Deleterious also exist.
Yes, but deleterious mutation reaching fixation can only happen from drift because negative selection would
Yeah.
actually.
It will produce, yeah, that part is correct. So actually N will play an important role. So to that extent, you are right, yes. But I will put everything in this umbrella of selective sweep. Actually, there's a larger umbrella. It's called hitchhiking, genetic hitchhiking. So selective sweep is so in the selective sweep, we have deleterious, beneficial, neutral sweeps. But there's a large umbrella. It's called genetic hitchhiking. There is a problem I will discuss in tutorial. Okay? So more generally, this is called genetic hitchhiking. Okay? Okay. Any questions? Yeah.
What happens like deleterious and beneficial mutation come together?
Yeah. Yeah. They're together, then what happens? Yeah, so then, yeah, I want to discuss that problem and I did not get time. So that's something very interesting. You know, we always talk about beneficial adaptation. But do deleterious mutations also have any role to play in adaptation or reduction of this diversity? Because deleterious are actually far more common than beneficial, no? So that requires more detailed discussion. I cannot do it in 2 minutes. So I will see if we can find time for the lecture. Yeah. Any other specific question? Yeah. Actually, you have to speak louder. The star is a neutral mutation. Yeah, zeros and ones are neutral. Zeros and ones are beneficial. No, zeros and ones are all neutral. They're just two types of alleles. One is a beneficial mutation. Okay. No, but then that question is different. No, here we are talking about neutral genetic diversity. How is the neutral diversity affected? If I did not have star, these are all neutral. Zeros and ones are neutral, no? Because they're different. Somewhere there's zero. That's the exercise we did at the beginning of the class. right? So there is a diversity, and all are neutral, right? If I make if one of them is beneficial or deleterious, that's what I was trying to say, right? And I want to know what's the effect of this recombination and selection and drift and this mutation. We did not say much right now, it just came once, and I'm going to turn it off till something happens, right? So the effect of selection, drift, and recombination. What's the effect of that? That's the selective sweep. And the key thing that I want you to remember, because I need this on the last lecture, is this is a large and rapid change in the allele frequency due to new mutations. Okay, I think I should stop here. Thank you.